Hello and welcome to the video. Today we will be looking at pulleys, and specifically we will be looking at a very common problem that then leads to more complicated problems down the line. So here are our test subjects, I guess. This is the first pulley, and as you can see it has a mass of 35 grams. And this is the second one, which is identical except for some weights have been removed, which gives it a mass of 17 to 18 grams, or about half of the other pulley. And here is the setup. As you can see, I just have one pulley attached to the ceiling and one end of the rope also attached to the ceiling rigidly. And here is what that results in. As you can see, when the two pulleys when one has half the mass of the other, they're stationary, and even if I move them to another position, they still remain stationary. So let's look at why that is. So here I have a free body diagram of the two masses, and as you can see, they both experience the same tension since they're connected by the same rope. And here are their equations for Newton's second law. You can see that mass times acceleration equals tension minus the force of gravity. Now for the pulley on the left, there's two forces of tension pulling it up. So for the example we just saw, you would imagine we want the acceleration to be 0 for both of them. And it makes sense that when the acceleration for one is 0, the acceleration for the other is also 0, since they're connected by the same rope. So this is what we end up with. Get that 0 equals tension minus mass 1 times gravity, and that 0 equals 2 times 2 tension minus mass 2 times gravity. And with some simplification, we get that mass 2, for this to be true, mass 2 has to be equal to twice as much as mass 1, which is exactly what we saw in the video. And I encourage you to take the time and try to do this derivation on your own. It's really not overly complicated. So now let's go into tracker and let's look at a more interesting case of this motion. Here's tracker, and first, as always, let's just let the motion play out. And as you can see, both of the pulleys move with a constant velocity. The one on the right moves downwards and the one on the left moves upwards, which is what we would expect from a pulley system like this. And you can see that the pulley on the right, from the tracks, they're much further apart, so the pulley on the right moves quite a bit faster than the pulley on the left. And knowing this, let's go back to the presentation and let's derive just how much faster it is moving and why. So here is a diagram of the motion we just looked at. As you see, we have S1, which is the length of rope from the top pulley down to the mass 1. Then we have S2, which is the length of rope from the top pulley down to the bottom pulley, and S3, which is the length of rope from the bottom pulley up to the ceiling. Now, one thing I want you to notice is that the length of rope from the top pulley up to the ceiling is always constant. As such, we can say that S3 is equal to S2. And you will see why we can do this in a second. So then we can say that the total length of rope is equal to S1 plus 2 times S2. Of course, disregarding any length of rope going around the pulleys themselves and the rope going from the top pulley up to the ceiling. And the reason we can disregard this is because what we really care about is what happens when we differentiate this. We get that V1, which is the rate of change of the length of rope from the top pulley down to the mass 1, plus 2 times V2, which is the rate of change of the length of rope from the top pulley down to the bottom pulley, is equal to 0. And notice that since we differentiated, if we included these constants, the length of the ropes around the pulleys and the length of rope from the top pulley up to the ceiling, those would have just turned to 0 anyway in the differentiation. Now we can differentiate once again and see that 0 equals A1, which is the rate of change of the length of rope from the top pulley down to the bottom, down to mass 1, plus 2 times A2, which is the rate of change of the length of rope from the top pulley to the bottom pulley, is equal to 0. Now, notice that I said rate of change for V and rate of change for A. These also correspond to the velocity and acceleration of mass 1 and mass 2 respectively. But since we're looking at the length of rope and the change of that, it is more appropriate to say rate of change and rate of change of rate of change. I just thought I should point that out since you will see different people say both of those, and I just wanted to make sure you know what's going on in that case. So from this, we can derive very easily that V2, so the velocity of mass 2, or the rate of change of of S2, is equal to negative 1/2 that of mass 1 and S1. Likewise, A2, so the acceleration of mass 2, and the rate of change of of S2 is equal to negative 1/2 that of mass 1 and S1. So now, here is the data we got from Tracker that we looked at a little earlier. So you can see that pulley 2 and pulley 1 both go in opposite directions, and that pulley 2 has a much mellower slope than pulley 1. Also notice I normalized the data so that both of the pulleys start at 0. As you saw in the video, they didn't quite both start at 0. They started at different positions, but this is for illustration purposes, and the data still applies anyway. Then notice the yellow dots on the bottom here. These represent the ratio between pulley 2 and pulley 1. And notice that all of the dots, lie approximately on negative 0.5, which is what we would expect given that pulley 2 moves at half the speed of pulley 1. And that is it. Hopefully you gained some intuition about pulleys, and good luck in your studies, and have a great day. Goodbye.